After you said that CO2 is pretty much created by the production of everything,
Yeah.
is there some way to like tackle this legitimately, or do you think?
Well,
I mean, some people think this is the metaphorical train that we're putting our heels down to stop. Do you think there's truth to that, or do you think that this is a accomplishable thing and a tackleable problem?
I think we have to develop the techniques for doing it. Let's go back to a more fundamental level of chemistry. What's going on? You're taking almost everything that we touch and feel and see and eat, and everything is a carbon compound. Plastics, your food, pharmaceuticals, the oil and gas you put in a car. A lot of the stuff we manufacture is carbon based, and we produce a carbon product that we want to use, and then ultimately we get rid of carbon waste. The carbon waste that we produce, CO2, is in its most energetically stable situation. So entropy is maximized, if you remember the concept of entropy in chemistry. Um, so if you're going to take a compound like CO2 and produce something useful out of it, it's going to take energy to do that. It's always now. Anytime you produce something, it's going to take energy to run the reactions. Even making plastic, you got to take some kind of crude oil input, and then you perform some heat to it or some chemistry to it, and you produce plastic or whatever. You're taking an organic molecule, producing something useful, and you're driving. I'm sure you're driving off in that process too. You're driving off some form of CO2. We can produce a technique for entrapping that CO2 and sequestering it. It takes energy to do it. Because why is it? I mean, even collecting up CO2 that you have liberated gaseous CO2 coming out of let's say a steel plant or a power plant smokestack or something like that. That CO2, if you decide that, okay, all I'm going to do is concentrate this and pump it underground, which so far has been the main answer when somebody says carbon sequestration, that's really what they think of right now. I mean, mineralization is sort of given a second look at, oh yeah, there's that too. But by and large, most people say, well, we've got the CO2, if we can concentrate it, then we can inject it underground. In other words, they look for a trap underground where they can try to store the CO2. But even doing that, you have to take a gas, which is, energetically a loose, stable particle, molecular arrangement, right? It's evenly distributed in a room, it's spread out to the shape of its container, like all fluids. You have to then concentrate that. So right now you're talking about energy, you're talking about pressure volume work to concentrate that gas down into something that you can then pipe, or pump to the field that you're going to inject it underground. So even collecting the CO2 out of a relatively concentrated area, like out of a flue stack, getting it compressed, getting it into a fluid that you can pump, and then injecting it underground, that takes energy. So any time that you're going to produce anything useful out of CO2, it's going to take energy to do it. And so it ultimately then becomes a cost benefit analysis of where you're expending energy anyway. And I haven't run those numbers, but I think what I'm trying to do with desal is like you're already spending tons of energy to concentrate that salt. I mean, that's not your goal in desal. Your goal in desal is to produce the fresh water, but the energy is going into pumping salt water through a membrane to produce fresh water as a result of that. You can almost think of that analogously as the energy of evapotranspiration, or evaporating the water, fresh water, off of a salt source, the ocean. That takes energy to do that. So it takes energy to produce a fresh water, right? But you also have the salt. So the net effect of expending that energy to produce fresh water is this concentrated salt product. Here is a way that you can take this liberated gas, run it through that, and immediately trap it into the water, as bicarbonate, and then ultimately into carbonate mineral. And that, to me, I think if you have, especially if you have those things working side by side on the same property, that could be energetically feasible. The process that I'm describing here of electrolyzing salt, we're right there. There's the energy that's input. That reaction is not spontaneous. It takes energy to do that. You literally put salt water in what's called an electrolyzer. It's an anode-cathode arrangement. You add an electric current to that. You're producing the products that I'm talking about, the sodium hydroxide, the hydrogen, and chlorine. And then separately, then you're running through the CO2 through that solution and producing bicarbonate. That process is spontaneous. In fact, Dow, one of the ways that I discovered this reaction on paper is I was reading about Dow Chemical, which was located in Michigan, and they were producing brine, and they were electrolyzing, forming sodium hydroxide. They sell it as a product, the sodium hydroxide. So they were electrolyzing brine out of the Michigan basin and producing sodium hydroxide. And they had some papers describing what they had to do to securely ship the sodium hydroxide so it wouldn't become contaminated. And I began digging, well, what's contaminating this sodium hydroxide? Why does it have to be airtight? Just atmospheric levels of CO2 alone. They're talking like the 315 part per million that I was talking about, the ambient CO2 concentration in the atmosphere, was enough to taint the sodium hydroxide in their containers, because it would cause some of the sodium hydroxide to go to sodium bicarbonate, which is exactly what I'm trying to do. I'm trying to make sodium bicarbonate, which is baking soda, basically. To Dow, this is not something they wanted. They wanted to sell raw, unadulterated sodium hydroxide product. But because their vessels were leaking, they were ending up with sodium hydroxide impurities in this material. So that goes to show you how effective it is.